Hello. So let's start with our first DRL algorithm, deep Q-learning. So a reminder, the idea in value-based RL is to approximate the Q values for a policy, so for policy evaluation, with a linear or non-linear function approximator with parameters theta. So in deep RL, it's just that we are using a deep neural network to approximate either the policy directly or the Q values. So in value-based deep RL, we approximate values, in general the Q values. The policy will be derived from these Q values using, for example, greedy, epsilon greedy, or softmax action selection over these Q values. So the policy itself will be parameterized with theta. The Q values are parameterized, and then you have a function of it to deduce the policy. What you learn are the Q values. As we saw last time, there are two ways of estimate the Q values. Either you have your deep neural network approximating the Q value of a single state action pair, or the neural network takes a state as an input and outputs the Q value of all possible actions. So the only change between these two architectures is how many neurons you have in the output layer. So with this setup, actually the actions can be continuous. You can have joint angles as actions, and you can always estimate a Q value for a particular continuous action. If you use this scheme with one output neuron per action, by definition you need a discrete number of actions. So this is what we are going to see in DQN. It only works for discrete action spaces. Later, with policy gradient algorithms, we will see that we can use this structure to predict the Q value of a single action. So how do we do this? So the first naive approach that will not work is simply doing Q-learning using a deep neural network as function approximator. So reminder of what we saw last time. We could just initialize our deep neural network with some parameters and have the same interaction loop over episodes, starting in a state, taking an action using a softmax or epsilon greedy over the estimated Q values. You take the action, observe how much reward you get and in which state you arrive, and then your loss function for the neural network will be to minimize the square of the TDRL, so reward plus gamma Q value of the greedy action in the next state minus Q value of the current action. If the state you arrive in is terminal, you break, you do another episode. So this thing I will omit it for now because it's always the same. So just for a fixed number of steps we do this iteration, and that will be implicit that at the end of an episode we reinitialize. So why is it not working? The problem is that the loss function is computed using a single transition. For deep neural networks, we need mini batches, so stochastic gradient descent, where we estimate the true expectation of what we want to minimize using k different samples. If you have only one sample, like in the previous algorithm, then it's called online learning, and that doesn't go well with deep neural networks. For linear algorithms, that's fine, but for deep neural networks, it's really not working. It's too unstable. The variance of the mean square error here is simply too huge. So what we need is to sample k transitions, build a loss function as an average over these k transitions, and learn from it. But which k transition should we take? If we look at the algorithm, we act over time. So we have a single transition to learn from at this step. One simple idea would be to not learn at every time step, but learn only every k steps, that we accumulate the quantity. And when we have enough transitions to learn from, then we build the loss function and we minimize it. So that would be using a transition buffer. The algorithm would look this way. Initialize your network, have a buffer of size k, where you will store transitions, state, action, reward, next state, for k different transitions. And then during learning, you select an action, take it, store the transition in the transition buffer, and every k step you will build your loss function as the average over the last k transitions of the TDRL square. Then you would differentiate it and train your network with it. So I omit the stochastic gradient descent part, that you need to compute the gradient of this. It's only implicit. Then you empty your transition buffer, and then you will do k other transitions, learn from them, and so on and so on. The problem is that it doesn't work either. The k transitions, when you do them sequentially like that, are not independent and identically distributed, IID. That's a condition for stochastic gradient descent to work. The k samples you put in your estimated loss function must be independent from each other. And here, by definition, because we act over time, they are not independent from each other. You can take the action at time t plus 1, only because you took that action at the previous transitions. Otherwise, you would not be in that state, and that would make no sense. So because you are acting over time, by definition, your transitions depend on each other. They are correlated. So that's a big issue, because your mini batches are not IID, and that means the SGD will not work correctly. That's a big problem, especially when you learn from video frames, because if you have, let's say, 30 frames per second in a game, the content will not change that much between 2 frames. Maybe the ball has moved from 1 pixel and nothing else has changed. So there's a huge correlation between 2 successive frames. The same for your action. When you're trying to catch the ball, you will go right for many steps until you stop and then maybe go left or continue to go right. That means all the transitions in your mini batch will have almost equal states, equal frames, just 1 or 2 pixels are going to change, and almost exact actions because you are going right for several steps. So that's something that deep neural networks don't like at all. It's as if when you have the MNIST dataset, so sample digits between 0 and 9, you were training your neural network on all the zeros first, and then all the ones, and then all the twos, and so on. That's not working at all. You will get a very bad performance in the end. In fact, you will have one exercise to get introduced to Keras, where you will try to do this, and you will see it's really not working. The only way to train a neural network is by sampling totally different digits every time. You feed the 3, the 4, the 2, and the 1 in the first mini batch, then the 9, the 5, the 6, and the 2 in the second mini batch. There's no correlation between them. It's not all the zeros and then all the ones. So that's already the main difficulty of RL, because in supervised learning, you have the data before you train. So you have a complete training set and you train offline. You're not interacting with the world while you are training your neural network. The dataset is fixed. So it's possible to be IID because the data is fixed and you just randomly choose k of them and use that to train your network. In RL, you are acting while you are learning. So in some sense, you create the training set during training. It's not available to you beforehand. That's online learning. We will talk in the end about offline RL, what happens when you have a data set to learn from. But the general settings, it's really online learning. Your agent interacts with its environment in real time. So in that case, our samples are not IID because we act sequentially over time that introduce a correlation. We have another problem in RL, which is different from supervised learning. Another characteristic of reinforcement learning compared to supervised learning that makes it much more difficult is that the targets are not stationary. In supervised learning, when you try to classify images into cats and dogs, the targets, the labels that you use for training and forming the mean square error are stable. The image of a cat stays a cat over the whole training, so different epochs. It doesn't change. It's not the first epoch, it's a cat, and then it becomes a dog suddenly. So that means you have a stationary problem. The distribution of the data doesn't change over time. And so that's something that neural networks appreciate. They can learn in a stable world, and that's what makes them able to solve the problem. In RL, the targets, so what the Q value should be in the end, so reward plus gamma, Q value of the greedy action in the next state, changes over time, because the Q value in the next state is also dependent on the parameters. So if you change the parameters of this Q value, you will implicitly change the target, actually this Q value for the next action. So that means instead of having a fixed target over time during training, and then in supervised learning, you can quickly catch up and reduce the error. Here you have a true value for the Q value of an action, so Q pi, what you're trying to learn, but your target, R plus gamma Q value, is not going to be equal to the target, because that's an estimate, which is also wrong. So you will try to catch up with something which is wrong, and then this thing which is wrong is going to become less wrong. So you catch up with it, and you have a kind of race between the two, such as at some point it gives up. So both estimate for with theta for the next action and the current action will be wrong and reach an equilibrium different from what the true value should have been. So it's a huge problem when what you're trying to approximate changes over time. Deep neural networks are bad at that. They need a stationary problem to really be able to minimize the mean square error. So let's have a look at a simple illustration of this problem. You have Q estimate, so that's what you want to produce, and it should minimize the error with a target, reward plus gamma next Q value. So you want to make this close to that. If you do it with gradient descent, then you will get to that position, but the target has moved. Then you try to minimize the error again, go to that position, but the target has moved again and again. So that means the optimization path that you are going to do will be something very weird. You are going to change, so go in one direction, the target will change, so you need to go in the other direction and back. And that's something that is very inefficient in terms of optimization. So non-stationary targets are a huge problem. The question now is how to solve these two problems, the correlation of inputs and non-stationary targets, so that we can actually use value-based deep RL.